Hello, and welcome to the 21st lecture in the Jabrah Reinforcement Learning series. So today we're going to start talking about deep QLearning, where we'll be using neural networks to approximate the Q-value function. So if you're already familiar with neural networks, that's fine, but if you're not, I'm going to link a course from the deep learning series where I introduce what neural networks are and how they work. So you might need to see that course first if you're not already familiar with neural networks. Having said that, let's get started. So we've already explored function approximators to estimate the value of a state when we're dealing with large state spaces. And this lecture is going to be following a similar theme, except that the function approximator here is going to be the neural network. So the idea is still the same. We're given a state and we were trying to find the value of that state, or maybe the value of a state and action pair. But this time we're going to approximate that value by making use of a neural network. So let me actually plot this. Rather draw it. So let's say we're given a state here. All right. Let's say we have, this is an example of a neural network. Right. So the input is the state, and it's going to go through multiple hidden layers here, right, and so on. And then we're going to have our output over here. So the input is the state, and the output is going to be the Q value, right, of the state and action. Let's say action 1, Q value of the state, and let's say action 2. Right. So that's the idea here. So we've got, let me put it like this. This is our input, hidden layer 1, hidden layer 2, and our output. So that's how we define our neural network here. So this is a problem whereby we have, let's say, two actions, A1 and A2, we're assuming they're discrete, and we're trying to find the value of the state action pair, and we say that we feed in the state to the network and it outputs the Q values for the state action pair, and the way we would choose the best action to take here is the same as we've always done, which is like taking the maximum of these Q values, right? We take the action that gives us the maximum of these Q values. Right. So this is fair and fine, but one thing you might ask yourself is, exactly when we're dealing with neural networks, usually we're dealing with them in supervised learning problems. So we deal with them in supervised learning, right? And an example of this is, say we're given, let's say we're given our target variables, which is y, right? So we would have a target. We would have a target here, which we term as y, and we will have our prediction, which is y bar, right? So that's how we typically do supervised learning, and we try to minimize the error between the target and the prediction. That's how we typically go about doing supervised learning, whether it's classification or regression. But in this case, as you can see, we input a state and we're getting some prediction, but we don't have a target, right? So how are we going to minimize the error between whatever is predicted by this network and some target value? Like, how do we actually learn anything with this, right? That's what we have to think about. So we have already spoken, when we introduced the idea of function approximators, we talked about how we can compute the value errors as follows. So assuming, let's say, we are given a policy and we're trying to find a policy pi, and we're trying to find, let's say, what is the value under pi, right, of this particular state, right? So we assume this is like the true value, we assume this is a true value here of v pi of s, right? And then we said if we're using a function approximator, we would compute, say, approximated value of s comma w, because we're parameterizing it by some weights w, and this would give us the approximate value, right? So if you're not familiar with what I'm talking about now, this is something we started talking about when we introduced the idea of function approximation. So you can look at lecture 18 and that should be clear. So we said that when we compute something like this, right? When we compute this, let's say the square of this would give us our value error, right? This would give us our value error, and we would try to minimize this, right? But the point is the same. We don't have the true value. We don't have v pi of s here, the same way we don't have target here. And we said that we could replace this v pi of s by an unbiased estimate. So in the case of Monte Carlo, we said we could replace v pi of s by using, so here v pi of s, right? We could replace it. So in terms of, let's say, we can use GT, which is the total return, if we're doing Monte Carlo, right? So if we're doing Monte Carlo, or if we're doing TD0, we could replace this by, if you remember, it's R plus gamma times V of S prime, right? So this could act as our target, right? So that's what we had talked about, like in the, this is just a recap of what we talked about in lecture 18. So now, in terms of this network, we need to define a target. We can't use the v pi of s, the true value, because we don't have that. And we're not doing Monte Carlo here. We're trying to do QLearning, right? So first of all, let's actually think about the update rule for QLearning. So the QLearning update rule is as follows. We said to estimate q of s comma a, we would say this is equal to q of s comma a plus alpha times the reward plus gamma, the maximum over all actions of q s prime comma a minus q s comma a. So this is how we said we would define this is the QLearning update rule. And we said this was essentially our target, right, in this formulation. And we can essentially treat this as our prediction, what we're trying to predict. So essentially, QS comma A is what we're trying to predict. This is the output of this network, right? Is the output here. And this like bootstrapped like R plus the maximum over all Q values of some state and action pairs. This is our target, right? So in the case of TD0, if you followed the lecture before, you'll know that our target was similar to this, a bit different because it was on policy. But here, this is our target. So of course, we haven't parameterized this by the weights, and I'm going to do that. Actually, let me do that now so that you see. So this is you assuming that this is the update rule for tabular QLearning. But if we're doing function approximation, we can rewrite this as follows. So we are trying to predict. What we want to predict is, let me write it in a different color here. We're trying to predict Q of S comma A, but this is parameterized by some weights, which I'll just define as theta, right? We can define them as W, we can define them as theta, but here I'm just going to use theta. This is what we are trying to predict, right? Which is the output of this network. It's QS comma A, right? But it is dependent on our weights, theta. And then our target here, right? Our target, okay, let me like so. So our target in this case is RT plus gamma, the maximum over all actions of Q, ST plus 1, comma AT, parameterized by theta, right? So it's the same function, the same formulation we have here, except that we're parameterizing by theta because we're using a neural network. We're doing function approximation. So this is essentially the same thing that we did before when we introduced function approximation before from lecture 18, right? So this is what we're trying to predict, and this is our target. This already comes with its own fair share of problems, but actually, because the way you can think about it is, okay, what we're trying to minimize, right? I'm going to write it in a different color here because it's going to change a bit. We're trying to minimize the error between our target, which is RT plus gamma, maximum over all actions of Q, ST plus 1, AT, parameterized by theta, minus, let's say, Q of ST, AT, theta, right? So we could take the absolute value or we can take the square, it doesn't matter. The point is we are trying to minimize the error between, we're trying to minimize the error between this target and this prediction, right? That's what we're trying to minimize. But this already comes with its own fair share of problems, right? And you might be able to identify them already, but in order to do that, there are a few things I'm going to note here, right? Because in the previous lecture, we looked at some issues we'd have using function approximators for off-policy learning and bootstrapping and so on. And introducing the idea of trying to optimize this using neural networks is going to introduce its own problems, actually, of its own. And the first one we're going to talk about is, okay, we are solving a supervised learning problem here, right? We're solving a supervised learning problem where our prediction is given, we input the state, and then we get this prediction here that we defined here, right? And our target, right, our target y is given here, right? So the first problem we would think of comes in the way that we would optimize this problem. So we talked about gradient descent, right? Where I'm not going to actually go through the entire process altogether since we've already covered it, but the idea here is that we're trying to minimize this error, right? We're trying to minimize this error by using this gradient descent method, whereby we take the derivatives and move in the direction opposite the gradient. But there is in a more practical situation, we tend to use a different version of gradient descent called stochastic gradient descent, right? So again, let me just clear something up. We want to minimize this error. We want to minimize this error, right, with respect to our weights theta, right? We're trying to minimize this error with respect to our weights theta. So we say that we could use something like gradient descent to do this. But instead, we're going to use a variation of it called stochastic gradient descent, which you might already be familiar with if you're already familiar with deep learning. But the idea behind stochastic gradient descent is that normally in gradient descent, we actually have to go through all our samples in order to update our weights, right? But in stochastic gradient descent, we select a few samples at random, right? Rather than going through the entire data set, because going through the entire data set is going to take a very long time if our data set is too large. So let's say we're given some data set D, right? So we have our data set here. We have a very large data set, 1, 2, let's say it goes up to like 1 million, right? So when we're actually making our updates, if we're using gradient descent, we actually let me actually write that as well. So if we're using gradient descent, right, we have to iterate through whole data set, right? So we go through the entire data set, we update our weight, like the first time. Then we go through the entire data set again, then we update our weights, and the process keeps going on like that. But in stochastic gradient descent, which is a more practical solution when handling this large data set, what we do is we sample randomly, right? So we sample randomly from here, and then we update our weights, and we continuously do that, right? So here I'm trying to introduce the idea behind stochastic gradient descent because there's a greater point that comes to this in relation to these neural networks. So one aspect of stochastic gradient descent is that it assumes that our samples are something that is known as ID, which means independent and identically distributed, right? So this is the assumption that we make when we're doing stochastic gradient descent. So it works well with samples that are independent and identically distributed. And the more that if we actually start working with samples that are all correlated, then it becomes actually problematic to use a method like this, right? And we already mentioned that gradient descent is not practical when we're using like very large data sets, since it will take forever. So having said that, stochastic gradient descent has this assumption, but we know that our samples are not independent, right? So our samples are not independent. We already know this. How do we know this? Well, because if you remember how we actually do how we generate an episode, we start from some state S, we take an action, we get some reward, we end up in some state S prime, we take an action, right? There's another action, we get some reward, right? And so on. This means that this state S prime actually depends on state S, right? There is from S prime to S, right? Here there is a dependency, right? Because being in state S prime depends on the fact that we were in state S and we took action A, right? So these samples of ours are not independent, right? So what we do, right, when we're actually learning, right, because if we feed the network the samples as is, like if we just try to feed the network the samples in order, and by that I mean as we're generating the episode, we just feed in the samples to the network, the problem is that the neural network will be seeing samples of just one kind, and as that's happening, it will tend to like forget everything else it saw beforehand, right? So which is why we need to try to emulate this randomness, and we do this by creating what is known as a replay buffer, right? And this is going to be very clear when I actually go through the pseudocode. So if you don't understand what's happening right now, that's fine. Just be patient and we'll get there. So the idea behind a replay buffer is that we store all our experience in this replay buffer, which would allow us to train on independent samples, right? Because we'll just be picking transitions from the buffer during our training. So in order to actually explain what's happening here, let me go through the pseudocode, right? So in the pseudocode, I'm going to explain what we're doing, what a replay buffer is, and how we're using it to create, at least have samples that are random in this case, or at least that are close enough to being independent. So let me just go through the algorithm for deep QLearning with experience replay. Okay. So the idea is that first of all, we initialize replay memory D, right, of capacity N. So basically what we're doing is we are creating, we're creating a memory here. So you can think of this as some kind of, this is D, which is our replay buffer. So it's acting as our memory, right? We're remembering something, and you'll see why we're remembering that thing, right? And it has a length of, let's say, n, right? We can store up to n items, from 0 up to n items in this memory. That's how it works, right? So we're going to initialize action value function. So action value function Q with random weights, right? So that means, yes, we also initialize we initialize our Q with random weights, right? So the weights are, as you know, that the neural network has its associated weights here, W1, W2, and so on. So we're just creating like a random initialization of our weights, right? That's what this means. So for episode 1 until M, we're going to do the following. So for each episode, we're going to generate an episode and we're going to initialize our state, right? So everything so far is pretty standard with most of the reinforcement learning algorithms we've learned, right? We initialize our state S, and for each time step, right, t is equals to 1 until, let's say, capital T, we do the following. So with probability of epsilon, right, because we do something like epsilon greedy, we select random action AT to allow us to do some exploration. Again, still pretty standard with most of the reinforcement learning algorithm with so. Otherwise, we select the greedy action, which is the maximum over all actions of Q star. Oh, let me just say Q of ST, comma A, that is parameterized by theta, right? This is essentially what we do. Okay, that's fine. Still pretty standard. So we either take a random action for exploration or we take the greedy action for exploitation, right? And then as usual, we would execute AT, execute AT, then we observe RT and ST plus 1. Right. So normally from here, what we would do is, given that we started an episode, we generated this sequence of events whereby we say, okay, we started from state S, we took an action, we observed the reward, and the next state is S prime, right? And usually what we would do is we would use this experience to update our weights using some formulation, right? Because again, the goal here, if you remember, is we want to minimize this error, right? Where this was target and prediction. So that's what we normally do. We would use this thing that we this episode that we started, like we initialized state S, and we took an action, and we observed the reward, and now we're in the next state, and would expect to update our theta value. But instead of doing that, we're going to store this transition so the transition st, at, rt, st plus 1, we're going to store this in D, right? That means we will continuously store these transitions here. So we have this transition st, at, rt, st plus 1, right? Or actually, let me write this more generally too. We have the first transition, let's say s, a, r, s prime. Then we have another transition, let's say s from s prime to, we take a different action, we get a different reward, maybe end up in s double prime, right? Let's say we're just storing these different transitions, right? And so on and so forth and so forth and so forth until maybe we reach maybe our nth transition, well, I should say n minus 1, yeah, would be something like s to the whatever. Well, I mean, this part is not as important, but the idea here is that we observe a transition, we store it into memory. We observe another transition, and then we iterate again, right? Because after storing this transition, then st, right, is equals to our st plus 1 or whatever. So the idea here is that we started at some state, st, and then we took an action, observed a reward, ended up in a new state, st plus 1, and we stored this into memory. We store the next, and then we do this again, we store the next transition into memory, and so on. So we'll continuously do this, right? And we can do it like at least up to n times in this case. And then after doing this, what we can do is we can sample random mini batch of transitions from D, right? So what this means is now we're at a point where we're trying to update our weights, our theta here, right? And we do that by sampling a random mini batch of transitions. That means we come here, and when we just sample, so we just sample, let's say we take this one, we take this one, we take this one, we just sample a random mini batch of transitions, right? And then we update. We say yj is equal to, well, yj in this case, which is our target. So rj, if st plus 1 is terminal, or it's rj plus the maximum over all actions of q st plus 1 comma a prime, maximum a prime, let's say parameterized by theta, right? Okay. So we define yj. If it's a terminal state, it's just the reward, right? If it's a terminal state, this is just our reward. Otherwise, it's this expression, and this expression here is our target. If you remember here, this is our target. We're trying to minimize this error. So let's not forget that. We're trying to minimize the error between our target and our prediction, right? So this is our target. So essentially what we're doing finally is just perform gradient descent step on, say, either we can, okay, let's just do a squared yj minus q of st comma aj theta squared. So essentially this, we're just doing a gradient descent step on this expression that we're trying to minimize the error. So what is the takeaway from this algorithm? Most of it has been standard. The only difference is that what we're doing is the difference starts here. We start storing every transition we made into memory. And after doing that, say a couple of times, and then we sample a random mini batch from these transitions. The reason why we're sampling is because we don't want our samples to be correlated to each other. We don't want to just update every single time we enter a new transition, because we said the stochastic gradient descent algorithm works better with samples that are IID, right, independent and identically distributed. So here we try to emulate that randomness by sampling, right, from our transition. So after sampling here, then we can compute our target, and after computing our target here, we can perform our gradient descent step and minimize this error, right? So, okay, this is all fine and all, but there is another problem at hand here, and you might already have seen it, right? Because we actually spoke about it before when we were doing, let me use a new page here. We spoke about it before when we actually started talking about this function approximation when we're doing semi-gradient salsa, right? So at this point, you know how the deep QLearning algorithm is working. It's just like your standard QLearning algorithm. The steps are the same, except that you're just storing these transitions and taking some random samples from the memory and using those to update your weight, because you want to play well with stochastic gradient descent. And again, this process, we called it experience replay, right? But there's still something wrong with the target here, right? So if we check again, let me write this here. What we are trying to predict and what our target is. Let's look at it once more. And we see this is Q of S, comma A parameterized by theta. And this is RT plus gamma, the maximum over all actions of Q of ST plus 1, comma AT parameterized by theta, right? So you see a problem here is that the target itself is depending on the network. It depends on theta. So both the predicted variable and the target depend on theta, right? So both this is parameterized by theta, this is parameterized by theta, right? And we're trying to compute the loss, the difference between the target and the prediction variable. So as you can see, this is a problem, because let's say we update, like we do our gradient descent step, and then we update the value of theta. So after updating the value of theta, QS, A is going to change, right? The value of QS, A will change because we changed the value of theta. But at the same time, because we changed the value of theta, our target is going to change. So what ends up happening is that we end up chasing a moving target, because every single time we change the value of theta, which is the only way we can change our prediction, we're actually inevitably changing our target, right? So it becomes very difficult to optimize this problem, right? So because we are chasing a moving target every time we update data, right? So this is a problem here. And how do we actually resolve this problem? Well, one way we do that is by defining two Q networks, right? So we define two Q networks, right? So the first one we define is called, we call this the main network, right? So we have our main network. Let me just plot it, say something like that. Okay, this is our main network. Okay, this is our main network. And then we have another network, so this is one main network. Then we have another network we call the target network. Right. So this is our target network. Right. So the thing is, between the main network and the target network, these are going to be identical. This will be identical. So what's the big idea here? So our target network is the same architecture as our main network, except that while we're going through this whole process, like when we reach this point, let me come back to the pseudocode, right? When we reach the point where we're trying to perform this gradient step, we're going to freeze the weights of this network. We're going to freeze the parameters, right? And we will copy them, let's say every k iterations, right? So let me show you what that means, in practice. So let's say, we have our main network, and this main network, what are we using it for? We start in the beginning. We have a theta, let's say theta I, right? So this is the initial values of our weights, right? It's theta I. Okay, we're going to copy this main network to the target network. So the main network and the target network are going to be exactly the same. So this is going to have the network parameters theta I, right? Okay, so that means the target here we're predicting would be, let me write it again here, would be, let's say Q S comma A comma theta I, right? And over here it will be the same. Actually, there's no need to write this down like this. Let me just say we started with theta I, then this is theta I. We've frozen the weights here, right? And then let's say in the next iteration, we sample again from our mini batch, we sample from memory, and we want to update the value of theta, right? So we will update the value of theta by doing gradient descent. And after doing an update, here, this becomes theta I plus 1, right? I've updated the weights, right? Now I'm trying to compute the difference between my target and my prediction. I will not update this, right? So here I did a copy, right? I copied my weights from my main network to my target network. Then I updated the main network, but I am not going to update the target network yet with the value of theta I, right? That means my loss function is actually going to look as follows, right? What I'm actually minimizing at this point, so let's say at this, let me actually So at this point, what I am minimizing is as follows. I am minimizing Q of S, A, theta I plus 1, right, minus, right, RT plus gamma maximum over all actions of Q of ST plus 1, AT, parameterized by theta I, right? So do you see the difference here? The difference is that in the previous case here, when we're doing it over, let's say here, theta was the same, right? So that's why we're chasing a moving target, right? But what we're doing over here in this case, theta is frozen, right? So when we update I plus 1, then this remains theta I, right? So that means for some period of time, this is actually the same. It's actually frozen. We're no longer chasing a moving target, right? And then I'll continuously update this. Theta I plus 2, theta I plus 3, right? And then every k iterations, right? After k iterations, I will copy the weights, right, from here. So if this is, let's say, theta k, then I'll copy the weights here to become theta k, right? So now I've updated the target, right? And now I'm chasing the new target, right? And then the process continues on and on like that. So in case you didn't understand this, the main point here is that we are trying to avoid chasing a moving target, right? So we freeze the network, we freeze the weights of the target network, right? And continuously update theta, right, in our main network. And then after, let's say, k iterations, we copy again the weights from the main network, the target network, so that we chase the new value of theta, right? This is the idea. So we end up with the following loss function. So our loss function looks as follows. So this is equal to RT plus gamma, the maximum over all actions of Q of ST plus 1, AT, theta I minus 1, parameterized by theta I minus 1, let's say, minus Q of ST, AT, parameterized by theta I, right? Let's say the square of this. So this is now what we are minimizing, right? So this is always using an older value of theta, right? So that means this will the target will stay constant for at least k iterations, right? So this ensures, let me write that down. This ensures target stays the same for at least k iterations, right? So for at least k iterations, our target will remain the same, right? And then because it's using an older value of theta, and then after k iterations, we update the target, right? We update the target, we update our theta, right? And then we do this again for another k iterations, and so on and so on. So this is just one way of, there are actually multiple ways of actually dealing with this whole problem of chasing a non-stationary target. But I hope this gave you a bit of an understanding as to why we would want to build two separate networks, like a main network and a target network. And if this is still not clear, that is fine. In a few lectures or from now, we will actually, or maybe in the next lecture, we'll actually start implementing this solution in PyTorch, and we'll be building our own neural network, and we will see like how we can define a separate main network and a separate target network, and how we can copy the weights every k iterations to ensure that at least for during that time we're not chasing a non-stationary target, right? So that we're not chasing a non-stationary target all the time, where it only gets updated every k times, right? So we're actually going to go through an example on how to do this, but hopefully this gave you an idea behind how we implement a deep QLearning algorithm and basically how they work. So thank you for your time. I'll see you in the next lecture.